Good morning. Today, I'd like to talk about the idea of circular orbits, or at least things that play the role of circular orbits. To begin with, let's look at the Newtonian orbit again. In this equation, u is 1 divided by the radial coordinate, g is Newton's constant, m is the mass of the gravitating body, and h is the angular momentum per unit mass. If we assume that we have a circular orbit, that means that r is a constant, u, being 1 over r, will be a constant, and as a result, both the first and second derivatives of u with respect to any variable will be identically equal to 0. That causes this equation to simplify considerably. U must be gm over h squared, so r will be h squared divided by g times m. For every value of the angular momentum per unit mass, there will be a circular orbit to correspond to it. In the case of a massive particle in a Schwarzschild field, we figured out that the equation for u is very similar to that in the Newtonian case, the only difference being the presence of this u squared term here. As before, let's look for pathways that have a constant r value, meaning a constant u value, meaning that du d theta and the second derivative of u with respect to theta must identically be 0. The equation that we get is as follows. Taking advantage of this fact and writing that u is equal to 1 over r, we are led to this equation. To make this a little bit easier to deal with, I'm going to multiply through by r squared to get rid of the variable in the fraction part of this problem. Multiplying through by r squared and rearranging terms, we find out that a constant times r squared plus a constant times r plus a constant must be 0. This is a quadratic equation for r, so it should be easy enough to investigate its solutions. Using the usual quadratic formula, r will be h squared over 2gm times the quantity 1 plus or minus 1 minus another quantity. That quantity is 12 g squared m squared over h squared c squared. This equation has several interesting features to it. If the term 12 g squared m squared over h squared c squared is larger than 1, we will be trying to calculate the square root of a negative number, and we won't get an orbit. That's a very interesting fact here. Under certain circumstances, the physical significance of which we'll look at later, you can't have a circular orbit. On the other hand, if this quantity 12 g squared m squared over h squared c squared is very small, then I can ignore it when I subtract it away from 1 and investigate what results in that case. In the case where we have the addition here, if I use the binomial theorem to expand the square root, the plus corresponds to r is approximately h squared over gm, which was the Newtonian result, minus 3gm over c squared, which under these circumstances will be small compared to the first term. The meaning of this is if 12 g squared m squared over h squared c squared is very small compared to 1, The result that we get for a circular orbit is for it to have r coordinate equal to h squared over gm, which, if we think in analogy to the Newtonian case, is what we should get. For the term 12g squared m squared over h squared c squared, small compared to 1, the other possibility is when we have the minus sign. Working through the algebra, we find out that r should approximately be 3gm over c squared. So in the case where the term that's being subtracted away is small compared to 1, there will be two orbits possible for each individual value of h. One of them is very close to the Newtonian value. The other one is not. It's this other thing. We figured out that the equation for a geodesic of a photon was this equation. Then once again, we ask ourselves, what would it mean for the r coordinate to be constant? That would mean that u is constant, du d theta. Also, second derivative of u with respect to theta would have to be 0, leaving us with this equation, which, if you write in terms of r and multiply through by r squared, tells you that r must be 3gm over c squared. That's the radial coordinate value of the new and different circular orbit for a massive particle. So our results are this. For photons, there's exactly one radial coordinate for which you can have a circular orbit. If you have a massive particle in a source child field that isn't very strong in a certain sense, you get two circular orbits for each value of the angular momentum. One, in the weak approximation, is very nearly the same expression as Newton's result. The other is very similar to the photon result. So even a light ray can be bent into a circular path by the gravitational field of a point mass. There's more to it than this, but we will talk about that later. I hope everybody has a good day, and I'll talk to you again soon.